two level system you can imagine as putting r particles or balls in just two boxes, two level. Two level means either one level or another level, either level 1 or level 2, which means either box 1 or box 2, you can think of that way also. So, typically when you talk about levels, people think about energy levels that keep on increasing. Here we are assuming that the energy levels are not like this. It is typically that is the representation of a two level system where energy increases. We will come back to that, and that also is very, very important. And you can look at the Introduction to Molecular Thermodynamics course in NPTEL by Shravani Tarafdar, who has given several examples using these two level systems and the practical applications with spin systems and other things. It will be it is elaborate and very clear, so you can look at that. However, here we are just assuming that the energy levels are same. So, it does not matter, energy does not matter right now, only thing is that the particle can be in either of these two levels, and we can either take the boxes to be distinguishable or not, and that will give rise to different statistics, but for the time being let us just take them to be distinguishable. So, there are two boxes 1 and 2, and there are r particles which has to be distributed. What we are going to get out of that? Once you understand that, we can go to more complex systems. So, or r, so I have taken n, fine. So, I have taken n distinct particles in two boxes. So, as I said again, r balls in boxes can be also characterized by many different ways. So, when I am talking about two boxes n equal to 2, essentially what it means is that it has either head or tail, right, and r particles will mean the number of coin tosses that I do, or let us say spins either up or down. I can take first spin, it can be up or down, I can take second spin, it can be up or down, third one up or down. So, that means the number of spins is like number of balls, and up and down is like boxes. If it is up, box number 1, down box number 2, as I said before. Now, possible microstates of 6 such particles is this configuration H T T H H H, let us say one possible configurations. How many possibilities we will get? We will get correspondingly, let us say spin is also like up, down, down, up, up, up. Now, let us take a two level system for n distinguishable particles, which means essentially that I have two boxes, two chambers, this and this, and these are the two levels that I talked about. In one level I have n1 particle, another level I have n minus n1 particle. Although all the particles look same, imagine that the particles are distinguishable, because remember what I said, that it may be our inability to distinguish the particles. However, statistics will come according to the distinguishability. So, let us assume that all these particles are distinguishable, and whatever the situation may be, n1 can be anything, n minus n1 can be the other thing, right. So, whatever may be the situation, let us put some particle in one box and some other particle in another box. How many possible ways you can do that? I can put one particle in box 1, therefore, 7 particles will be in box 2. Let us call that distribution A. That is one way of distributing n particles. I can have 2 particles in box 1 and 6 particles in box 2. That is another way of distributing it. Let us call that distribution B. I can have 3 particles in box 1, 5 particles in box 2, distribution C, 4 particle in box 1, 4 particle in box 2, distribution D. Now, if boxes are distinguishable, then I can have 5 3, which is same as 3 5 here. 5 3 and 3 5 are same if the boxes are indistinguishable, but they are different if the boxes are distinguishable. But here let us take boxes distinguishable. So, we came back to our initial situation where box and balls both are distinguishable. What statistics did we get? N to the power r. But when you came to combination and said that no, I am choosing the particles and then putting in the box, and in that box they are indistinguishable, we got a combination. So, it is like I have n distinguishable particles and I am choosing n1 out of that and putting it in one box, then rest will automatically go to the second box. So, then it becomes NC N1 kind of a problem. So, here each N1 represent a distribution as I said, and when n equal to 8 we can get following 7 possible distribution that I mentioned. Each one is a distribution, meaning just like our cards, these 4 cards we were distributing in 2 hands. Similarly, I have 4 particles, I am distributing in 2 boxes, just like that. 4 particles were indistinguishable, 4 particles were distinguishable, but when I distribute them in one hand, they are indistinguishable, in this hand this particle. So, it does not matter whether this card came first or this card came first, like you just look at the top part of it once I put in the box. Once I distribute it, you just look the top part of it. Okay. So, in that situation I have to only choose these 2 out of the 4. So, I choose just 2 out of the 4. How many ways I can do that? 4C 2 ways, 4 choose 2, and that is what is given here, that is my W. So, NC N1 is nothing but factorial n divided by n1 factorial into n minus n1 factorial by the formula itself. So, this is n choose n1. In this particular formula it is okay for any number of particles, it can n1 can be anything as long as it is not more than n. So, therefore, every distribution, so I denotes the distribution. So, every distribution will have an W associated with it, and that W is written here. So, this W corresponds to choosing n1 equal to 1 and rest of the particles will be in the other side. Then this distribution corresponds to choosing 2 particle and keeping it in one box, 6 will go to the other. This distribution will say that okay, choose 4 particle, put in a box, and the 4 can go to the other box. And it turns out that if you look at these numbers, then distribution D in which you put half the particle, see out of 8 particle, half the particle in one box and half the particle in the other box becomes maximum. So, that I can call as the most probable distribution. Why it is most probable? Because we can calculate the probabilities associated with each distribution. What will be that probability? That probability will be, let us say I can calculate the probability of D. Probability of D will be 70 divided by the total number. So, total number is 254. So, that is the probability of D. What is the probability of A? It is just 8 by 254. So, therefore, if you see probability D is most probable. So, sorry, distribution D is most probable. That is why it is called most probable distribution, where the half the particle in one side and half the particle in the other side. And we will see that it is so important that immediately it will explain physical phenomena that we observe all the time, and we have no way to explain without using these particular statistics or concept of probabilities or concept of microstates. Again, so when I am calculating, when I am talking about W, they are nothing but microstates. So, this particular distribution has 70 microstates, this particular distribution has 8 microstates, and automatically from that you know that entropy of D will be more than entropy of A or any other for that matter. So, such and wonderful thing the statistics is, and immediately can explain to us that why entropy will increase in certain situations. So, here as you can see, if you start with A, 1 particle in one side and 7 particle on the other side, it will go towards B, it will go towards D, which means that particle will diffuse to the other side, and that is precisely the reason that when you have that incense in your room in one corner, it goes all over the room and does not stay in just one corner, because going all over the room is most probable situation rather than staying in one corner. So, just knowing that will be enough to understand that. So, we are going to show you an example and a direct example from simulations, computer simulations, and show you that how the effect of microstates or effect of entropy is driving a change in a system in which a gas molecule expands from one side of the box to the other side. So, before I show you this example, I would just like to point out that this is a simulation is done by Raman Kumar Singh. He is my PhD student and he has used the computer simulation techniques to do that with some tricks, ingenious tricks to have the cover the boxes and things like that, and then along with my other student Abhijit has taken out the image and put it. So, I will show you that. So, this is a GIF file. So, initially you see all the particles. So, there are 210 particles, all the particles were on the one side, left hand side, denoted by the height of the bar, and you see these particles do not interact with each other, there is no concept of energy at all. Only thing is that there are these boundaries which is denoted by this blue line, the particle cannot cross that boundary, and there is a small hole here, as you can see, only particle pass through that. So, initially all the particles were on one side, the hole was closed and we took out the hole at t equal to 0, and then what happened is that the number of particles started changing. This number you can see from here, and also it is represented by this bar diagram. You see now that earlier 210 particles are on one side, there was nothing on the left box, now these bar heights are almost equal. You see that this situation is governed only by entropy, because there is no attraction of this box on these particles at all. If at all they and these particles do not interact with each other. So, there is no reason for this particle other than entropy, increasing entropy, to come to this side. So, which clearly indicates that when we take n1 as 105, the entropy or number of possibilities become more, and therefore, the entropy is more, and here you cannot distinguish the particles, but these classical trajectories are distinguishable by the fact that we can track them from their initial position and momentum, and that is the reason that they are inherently distinguishable, giving rise to this situation. If they were truly indistinguishable, then we would not get that statistics that we are getting from this particular simulation. So, let us do some calculation. So, here it is n equal to 210 and n1 is 105. If we do that, when all the particles were in one side, it is NCN, and that is only 1, you can see, and when half the particle has gone to the other side, then n1 is 105, and that if you do, it is a big calculation. So, W is 210 factorial divided by 105 factorial multiplied by 105 factorial, that is the calculation, and that gives 9.05 into 10 to the power 61. I will show you the calculation here itself. So, 210 C 105, you see 9.05 into 10 to the power 61. What did I write? Yeah. So, that many possibilities it is going towards. Does it mean that there will be no systems where 104 particle in one box and 106 particle? Yes, that possibility is also almost equally okay. For example, if I do 104, that is also 61. If I do 100 only, that is also 61. So, deviation of 5 particle does not matter. Let us do deviation of 10. So, let us do 115, 61. Let us do 10% deviation. So, let us say 21. So, 21 minus 105 will be, or 21 plus 105, the same thing is 122, it becomes 60, 1 order less, and do 20% deviation, let us say, or 25% deviation. So, what will be the 25% deviation of 105? Is approximately 25 deviation or 30. So, let us call 135. So, I am saying that 135 particle in one box, and how many it will be 65 plus 10 is 75. So, 75 in the other box is 58. So, 100 times less than that. So, like that you can see that the probability is that there will be deviations from this 50-50 will be lesser and lesser as the more deviation takes place. Now, so it only means that initial entropy will be 0 because there is only one possibility. So, ln 1 is 1 because remember S equal to kb ln w, we already said kb ln w. If w is 1, then S is 0, and then when it goes to the other side, then it gives this much kb, because it is kb ln this quantity and it gives that. However, I would just like to point out that it is not just 105 that will give us this entropy. There will be fluctuations around that, and let us say there are 100 other configurations will give us, and that will not change much. Let us say I take 100 such configurations. So, it will be 100 multiplied by, so in that case it will be, I consider 100 more configurations. So, it will be 100 multiplied by, or and taking approximately equal of their w's, it is not going to change even if I take 100 configurations around the midpoint. So, that is the idea that it is not going to really be different. So, only one configurations in the middle is good enough. Now, what if we had only 2 particles? What if I had only 2 particles instead of 210? What if I had 2 particles? Could we see that 2 particles are going as 1 and 1? Let us see that. So, here I have 2 particles on one side of the box, and as you can see from the bar chart, 1 and 1 is favorable and they are there. But in certain cases, when I started with, I had this bar full and this bar was there. Now, these 2 particles have come to the one side. So, with 2 particle, I often get a situation where one box remains empty, another box remains full. With 210 particles, I never encountered a situation in which one box were totally empty. It was half and we were fluctuating around half. Here, I have 2 particles, you can say okay, you have only 2 particles. So, if the particle goes to the other side, then it becomes empty. Yes, that is right. Also, it is right that the probabilities of having 1 1 and probabilities of having 2 on one side, they are not very different with 2 particles.
For example, let us talk about this 2-state system where there are 2 particles in 2 states. Now, we can have 3 different situations where both the particles are on the left hand side of the box and no particle on the right hand side of the box, or one particle in each of the sides of the box, or both the particles on the right hand side of the box. Now, Wt is the number of microstates when both the particles are on the left hand side of the box, and that will be 1. W1 is when both the particles, one particle in each box, that will be the W equal to 2, and also no particle on the left hand side of the box will be a situation where W will be equal to 1. So, if you calculate the probability, then probability that both the particles will be on the left hand side of the box will be 1 by 4. No particle on the left hand side of the box will be 1 by 4, and one particle in each side of the box will be 2 by 4 or half. Now, here the figure shows that if you do a simulation long enough, then eventually in equilibrium, or when it will reach the steady state, then you will get 0.5 or half probability for one particle in each box, whereas 0.25 is the probability when you will find 2 particles are either on the left hand side or on the right hand side of the box. Although the probability here is double when the 2 particles are on both sides of the box, is double than when both the particles are on the same side. However, it is not overwhelmingly large compared to the one we see for a large number of systems.
The probabilities were extremely large for half compared to situations where there was nothing on one side. So, therefore, as you can see, the number plays a very important role. So, I am talking about 2 particle and 210 particle. I have not gone to 10 to the power 23 particle. You imagine what will be the situation there. I will give you a glimpse of that in a moment. So, this is what is meant by when a system is left to itself, it goes towards maximum probability or goes towards the most probable distribution. So, when I left the system with 1 particle in one box, it went to a situation where it is most probable. That means filling both the boxes with more or less equal number. That is the most probable situation. So, it went there, and that is what we call as entropy. So, entropy then is nothing but just going towards more probable situation. It is as if it is destined to go. It is the possibility is there, and therefore, it is going. There is no thoughtful choice is involved, and that is why people say that life is nothing but a chance, because there is a possibility that and you go and avail that possibility without thinking. I have possibility to go any over in the campus, so I am just aimlessly roaming around and being found at all the different places. If I did not have, if I are confined in the room, the possibilities will be limited only to the room. So, therefore, entropy is not just confined to the problems of science or chemistry. It can be associated with anything that we can think of, because it is at the end nothing but the number of possibilities.